So, greetings everyone. Myself Aadhar Gupta. I'm from Applied Cognitive Science Lab from Indian Institute of Technology, Mandi, and I'm going to present our work on learning from single and multi-human intelligence via cognitive and reinforcement learning. So we know nowadays AI has been performing quite nicely in training artificial agents to achieve intelligent behavior, achieve good behavior. And one of the very widely utilized approaches for that is trial and error approach. And reinforcement learning, which is not a new term to anyone, is actually following this approach and achieving quite good results in various tasks. However, one more approach which has been used as well is learning from human behavior or learning from human demonstrations. And imitation learning has actually made this technique very popular. So in this work, actually, we'll be focusing on learning intelligent behavior from human demonstrations. Now, there are certain problems with human behavior demonstrations, basically. So, as we know, that each person's behavior tends to have some personal biases and individual specific noise. This noise means, suppose someday I'm in a good mood, someday I'm excited, someday I'm feeling low, or I just want to do something in different way, or there are some things which I tend to do more often than other things. They might not necessarily be the correct way or the better way. It's just that I like to do that. So every person has that some unique tinge to his or her behavior. Also, such noise or biases actually increase the complexity of the data. They might confuse the model, that what the model should learn, what the model should not learn, and it masks the model to learn the actual relevant information, the actual good behavior from the whole human behavior that the model sees. Moreover, as each person has some individual, some signature style of doing any task, right? So there may be some behavior patterns that are present in a large amount in a person's behavior, whereas some things might be totally missing out. So the model is limited to what it can learn from a single person's behavior. So in this study, basically we focused on exploring that how we may be able to use the data of multiple people to actually get rid of these drawbacks and get rid of these biases. I mean, overcome these biases, these noise. I mean, they will be anyway, they will be there, but how we can help our model achieve better results and surpass these noises, the impact of these noise, and understand the more relevant and the more useful information present in the human data. So let's see the methodology that we followed. So beginning with the experiment design, the task that we took was the cardboard problem. It is a very widely known problem where we have a box, a cart basically, which can move left and right on this platform. And there is a rod which is connected to this box at one end, whereas the other end is totally free. This end can rotate left and right. Basically, it can topple. And the task of the user is to move this cart left or right and using the inertia to balance the pole and prevent it from falling. The larger the time the player can prevent this rod from falling, the better the player is set to play. So the terminating conditions were that the angle of pole with the vertical becomes greater than 30°, then the episode would finish, or the cart would actually exceed the platform dimensions. These were the two terminating conditions. And we put some rewards for the various actions the human would play. So for every action which did not lead to the termination of the game, the player got a reward of 0.1. The score was increased by 0.1. And as soon as the terminating condition was reached, the score of -5 was given. And the current situation in the game was extracted using these four parameters: the cart position, that what is the coordinate of the cart; the cart velocity, the velocity with which the cart is moving left or right; the angle that the pole is making with the vertical; and the pole angular velocity. Now coming to the models that we've used. So in this study, we have prepared two models. The first one is a cognitive model, instance-based learning. So this model is actually derived from the quite popularly used model, that is ACTAR. Now ACTAR has been used very widely, but ACTAR is quite parameter rich. So sometimes it becomes very complicated to handle. So many researchers have actually tried to extend ACTAR such that its complexity could be reduced, but its efficiency and performance could be maintained. So, instance based learning is one of such approaches. In IBL, instance based learning, the information of past experiences is stored in the form of tuples of situation, decision, utility. Situation means the current state, the current scenario that a person is facing. The decision means the decision that taken by the user, the human. And in this case, because we are making him play a game which is having two actions left and right, so the decision here would be the left action or the right action. And the utility means basically how good that action was, how useful that action was. So in this case, the reward earned becomes the utility. So one experience of the human player, the human data contains the situation, the vector of four parameters about the card pole, the decision the player made, and the goodness, the reward the player obtained after taking that action. And the decision making in IBL is actually based on these four pillars: shortlisting, activation, probability of retrieval, and blended value. Now, for shortlisting, let me give you an example. Suppose I'm running on a football field, a wet football field, and I want to, make a sudden jump, or I want to make a sharp left turn. So I will recall my previous memories and decide that what would be the best way to do that. So when I will recall my previous memories, I will not recall my memory in which I'm studying in my room at night or in which I'm talking to my friends, right? Because those memories are totally irrelevant to the current situation. I will only recall the memories where I was running on a wetland or when I was running on a grassy field because they are more closely related. So the first step of the decision making process is to eliminate all the irrelevant memory tuples and shortlist the ones that may be useful for contributing to the decision making. The next three parts, activation, probability of retrieval, and blended values, are as described over here. So in activation, we calculate the weightage of each memory experience. So this is calculated using these three terms. I won't be able to go into the detail of each and every term used over here because of time foundation, but I can give an overview. For more details, kindly refer to the paper. So activation uses this term called base activation, and this term called similarity term. So this similarity term actually gives us the similarity of that memory experience to the current situation. This base activation actually is used to compute the recency is actually computed with the help of recency and frequency of the occurrence of an experience. That is, how recently has that experience occurred? Because by logic we can say more recent an experience is, so more relevant it can be to my current situation. Like what I was doing 1 minute ago can be more related to my current situation than what I was doing 1 day ago. So naturally, more recent an experience, the more relevant it becomes. And the another factor is frequency. Like if some experience is occurring again and again, then it might be relevant to my current situation as well. Whereas something which occurs very rarely, like once in a day or twice in a day. And this term, that is called the noise term, is actually to impart some uncertainty, some randomness in the behavior. Just like a human maybe doing the same task multiple days, but every time that task is done a little bit different. It is not the exact same way of doing the same task because we are not robots. The next step is finding the probability of retrieval. So this probability of retrieval is actually a function of activation, as we can see over here, but it is a more refined form of calculating the weightage of each experience. As we can see, this formula actually resembles like softmax formula. So where we calculate the weightage of each memory experience to the ratio of the weightage of each experience to the entire weightage of all the memory experiences of that action. So this would give us a probability value, a fractional value from 0 to 1. And then coming to this third part, that is the blended value. So this is basically a score that we compute for each action. And whichever action is having the maximum blended value, the maximum score is chosen as the final decision. And as we can see, this formula actually resembles that of an expectation. So it is nothing but the expected benefit. This xi represents the reward, the benefit that is associated with the various experiences. So the expected reward that we can have by taking an action is its blended value. and whichever action is having the highest expected reward, highest expected benefit, we choose that action. So we prepared two types of models in this study. One was the model which was initialized using a single human's behavior tuples, a single human's behavior data. And in the study, we took 10 players, 10 human players. So there were a total of 10 single human models prepared. There was also one multi-human model prepared in which we actually sampled 1/nth of the data of each human and combined them together. In this algorithm, 1/nth means if suppose we are taking n number of players, then 1/nth fraction of the data of each player was used to create the final combined data set. As in the study, we have taken 10 people, 10 human players. So 1/10th of the fraction of each human's data is used to create the final data set. And the IBL model is initialized with that multiple human data set. It's called multi-human IBL model. The second model that we've used is the very popularly used deep Q learning network, DQN, from reinforcement learning approach. So normally DQN or reinforcement learning uses trial and error approach, but we tried something different. We actually initialized this DQN model with human behavior itself. So rather than, trying out different things with the environment and learning, it actually learns from the human behavior. So just a basic of deep learning network. There are two neural networks. One is used for predicting the Q value, that is a score for each action possible at a state. Another is a target network, which is actually a recent copy of the prediction network. It gives a little better approximation of that value that should be for a particular action, and the model tries to minimize the difference between these two networks so as to reach a optimized prediction. So this is the
Okay,
architecture
Aadhar,
that we use.
Aadhar, just
Yes,
took
sir.
5 minutes. 5 minutes.
Oh, okay, sir. So this was the architecture that we used. And again, just like instance-based learning, in deep Q learning also, we prepare two types of models, single human model and multi-human model. So for evaluating the model, we made the model play the game of cardpool, just like a human was playing. And then let's see what the results we obtained. So as we can see, the y-axis over here presents the score that was attained, and the score of 1 means for 1,000 steps the player was able to prevent the pole from falling over. Okay, so as we can see, for these are all models, as we can see. So the single the single human DQN model got an average score of 0.8. The single human IBL model also got a score of around 0.8, but slightly higher of 0.85. The DQN multi-human model got a score of 1.05, whereas the IBL multi-human model got a whopping score of 2.36. So the multi-human DQN model actually gained 30% over the single human DQN, whereas the multi-intelligence IBL model gained 177% over the score of 0.585 of single human IBL model. And also, as we can see, in both the approaches, DQN and IBL, there was an increase in the performance when multiple humans data was used. Again, to remind, the size of the data was almost the same. It was just the diversity in the data, the human sources used. And also we notice that the IBL multi-human data actually scored 125% higher than from DQN, although the single human performance for IBL and DQN was the same, which also shows the ability of IBL model to generalize over different humans data and find out the relevant information from different humans data was much more than of DQN. So to conclude this study, we actually focused on studying the effect of multi-human behavior demonstrations on performance of AI agents. Human players played the cardpool game, and we recorded their behavior in the form of situation, decision, utility instances. And we actually used random sampling to create a collective data from multiple humans data. And in both the models, there was an improvement in performance, whereas IBL actually performed much better than DQN for multi-human data. So that would be all. These are the references. Thank you so much. These are my contact details.
Okay, we have time for a couple questions, but real quick.
That word you keep using, cognitive, I don't think it means what you think it means.
Sir, actually, there are certain computational cognitive models, if you think that would be the right. So cognitive,
Cognitive means having to do with thought, and IBL certainly can be used to explain some psychological phenomena, but it's certainly not very much about cognition. It's simply a very simple retrieval mechanism. So I would remove the word cognitive from throughout your paper if I were you. Go ahead.
Yep. Really interesting talk. I like the breadth of methods you explored. One of the things that I have found myself thinking about was, so in the the cart pull domain that you were looking at in particular, time matters a lot, right? If you were actually playing the game in real time, then the amount of time you spend thinking, like the more time you spend thinking about what you're going to be doing, the more the pole is tipping, the more likely it's going to fall over. And so you reported the accuracy of these different approaches. I was wondering if you could comment on how quickly they were able to operate. Were you looking at them in real time? Were you giving them as much time as they needed to make their decisions and so forth?
Yeah. So, sir, actually, I would say that it was not the time, but actually it was the number of steps, sir. So we divided actually the game into frames. So at every frame, now it depends upon us that what is the time duration we want to keep for each frame. And actually we kept it very small, around very small difference was being created between each successive frames, and each of that frames was being fed to the model, and then model was taking a decision.
Right.
So
My
actually there
question,
wasn't
my
much
question was
difference.
how much did you look at how much time each of the different models was taking to make the decision? Did you give each of the models the same amount of time to make the decision, or did you allow the models to take as long as they needed to make those calculations?
Okay, I got it now, sir. So, sir, the models, the time was not the constraint. The model got all the time it needed, then it would make a decision, and then that decision would be fed into the game.
Okay, so interesting. And so maybe as a direction of future work, if you're continuing to work in this cart pull domain, it might be interesting to see how those methods are comparing in terms of time, and how well they might, how the differences in performance might change if you're operating in real time rather than not. Interesting work.
Yes,
though.
I got it, sir. Yes, sir. Thank you, sir. That was a nice point. Thank you.
Okay, great. So we have a couple of questions on the Slack. We're only going to have time for one. A question from Eric Son says, are you saying that different humans have different ways of performing the pole cart problem? Since there's an optimal control strategy, please explain how those strategies would vary. And a quick answer.
So, sir, even though it appears that the task is simple and there's just one way to do something, but still, for different people, we can have different reflex time, right? And the different way they press the key, as in this case, that may be significant. So, for some people, they may be very quick in, clicking a key. Some people might be clicking the key very hard, so it may take some time for them to remove the hand if the rod goes the other side and then switch. For some people, they may like to let the rod go over a little and then push it back further. Some people might like to just maintain it at the very vertical. So for the same task also, there may be slight differences in the behavior of people. And what actually we found out in the study was that if actually the model got a glimpse of the behavior of each people, so it can know, okay, in different situations what would be the optimal way to do. Could I answer your question, sir?
I think so. In any event, that's what we have time for. Okay, so let's thank Aadhar and all of our speakers in this session.
Thank you so much, sir. Thank you, sir.